Hello Internet, and specifically my Algebra 1 students. Welcome to what I hope is a mega exciting video on quadratic functions. In my class in Algebra 1 this year, we've looked at exponential and linear functions. So with this video, I just want to introduce the idea of a quadratic equation, the idea of a parabola, which is the shape given by a quadratic equation, and some of the characteristics that you can find with these types of equations. So what we have here is the parent function of a quadratic equation, which is y equals x squared or f of x equals x squared. This is the simplest quadratic that you can encounter. It has a few characteristics. One I've already mentioned is it gives this shape, which is called a parabola, and it would be a parabola if it's facing up, or as we will see in a few minutes, if it's facing down, it's still a parabola, just like a line is always a line, no matter what its slope is. Unlike linear functions, this does not have a constant slope. Okay, here we're going down, we are decreasing, and then on the right side of the y-axis, we are increasing. So that's one thing that's different about quadratic functions and linear functions. It's similar to exponential functions in that the slope does change, but for exponential functions, which I will refresh your memory here, that's something like y equals some number raised to the x power, this blue function here. We can see that for this one, while the slope is not constant, it's constantly changing, the slope for this particular function is always positive. This is always increasing, or it would always be decreasing if it were reflected across the x-axis. But for quadratics, they change. We're decreasing and then we are increasing. So that's one unique thing about quadratics compared to some of the functions we've seen so far this year. What I've done here in Desmos is I have made what at first look may appear somewhat complicated, but it's really not, and I'm going to walk you guys through this. I've got these sliders in for these values such as a, h, and k. You can see here a currently equals 1, h equals 0, and k equals 0. So if you were to substitute in 1, 0, and 0, you would see that this function is actually, which I'll show here, actually exactly the same as what we have with the red function. And you can see that if I display it like this, you can see that the red function is right behind the blue function. Okay? But what happens if I were to change, let's say k? So I'm changing this value. I'm going to, right now I'm adding 0 to it, but what happens if I were to add a positive 1 to it? Notice what happened to my graph. So I was here, and now the parabola is shifting vertically, or vertically translating 1 unit. That's the terminology we would use for this, a vertical translation. So it's shifting up as k increases, and if k decreases, as you might expect, it will be vertically translating down. Okay, so that is pretty straightforward, I believe, and we'll practice this some more in class. But that's a vertical translation. Changing this value of k would be a vertical translation. Now h, notice that I'm subtracting h here. With k I was adding it, with h I'm subtracting. So if I make 0 for h, if I make that a positive number, in my formula up here I'm actually subtracting 1. So keep that in mind as I play with this slider. So here I'm going to take this over to 1. So x minus 1 squared gave me a horizontal translation to the right. Let me do that one more time for you. From 0 to 1 gives us a horizontal translation. And if I continue on with a larger positive number that would be subtracted, it's going to give me a larger horizontal translation. I'm moving further from the origin. If I make this negative, so here I am back at 0 at my origin. If I make this negative, such as -1, x minus a -1, so really this is x plus 1, I'm shifting to the left. This is a horizontal translation, a horizontal shift to the left. So that's what changing h does. It gives you a horizontal translation. Changing a, right now I have a equal to 1. If I make this greater than 1, we can see that my parabola is getting skinnier, you might say. But in mathematics, we call this a vertical stretch. So you can imagine that being a rubber band. Imagine somebody stretching, pulling up on that rubber band so that it's getting skinnier, getting thinner. It's being vertically stretched. And that's, once again, when a is greater than 1. Okay? When a is in between 1 and 0, so some fraction or some decimal value, we can see that it gets squished, it gets compressed. You can imagine a really heavy weight being on top of this parabola. Something sitting on top of it, it's pushing it down, it is compressing it. So when a is greater than 1, we've got a vertical stretch. When a is in between 0 and 1, we have a vertical compression. Now something interesting happens if we go below 0 here. And that is that we reflect across the y-axis. So this would be the mirror image of the red function. Y equals, or f of x equals x squared. Here we've got g of x equals -1 times x minus, in this case, 0 squared plus 0. So this is really saying y equals -x squared. The red parabola is y equals positive x squared. And here the same rules apply. So if we go to a value which is further from 0, so past -1, -2, -3, etc., we get a vertical stretch. Something in between -1 and 0, we get a vertical compression. So the same idea. And we'll practice this more in class. I don't expect you to be an expert on this after watching this video, but I want you to have in mind that a parabola is formed by a quadratic function, and a quadratic function is something where the independent variable, the highest exponent, is a 2. So x squared. You will always see x squared with a quadratic function. Quadratic function always gives you a parabola. That parabola can be vertically translated, horizontally translated, reflected across the x-axis, and vertically stretched or compressed, but it is still a parabola. The only other thing I would like to point out at this particular time, well, there are two things actually that I would like to point out. One of which is, how do we actually get this shape from this function, x squared? How are we ending up with a parabola? So let me turn this into a table, and we can see how we are getting a parabola. If you plug in -2 for your x here, -2 squared, so -2 times -2 is obviously 4. That's where this point comes from. -1 times -1 is 1. 0 times 0 is 0. 1 times 1 is also 1. And 2 times 2 is 4. So squaring values, no matter what type of value I plug in here, it's going to give me a positive output. So no matter what my input is, or what my x value is, my output, or my f of x in this case, will be positive. Okay, to give you another example, maybe -3. -3 squared is 9, which is right here, which, if I plug 3 in, hopefully you guys are seeing the pattern, 3 squared would give me 9 also. So notice they are exactly the same outputs, even though we've got two separate inputs. And that's, if you continue doing that, even with fractions or really large numbers, you're going to end up with this sort of shape. This is a symmetric function because you could cut it in half here, fold it over, and it would be perfectly symmetric to itself. The The final thought that I want to leave you with, I'm about 10 minutes into this video, so you're probably starting to lose you, I imagine. The final thought I want to leave you with is about domain and range, which we have started to talk about with other functions. So you may remember that domain is always about the x values. It's about your input into a function. And for this function, we can plug in any value for x and get some sort of an output. So I could plug in here something crazy, maybe negative 1075, and I'm going to get a number. Now it's a really big number, but I still get a number. I could plug in something very small, negative 0.0072, and once again I get an output. It's a very small output, but I get an output. So the domain for this function is actually all real numbers. You could plug in any real number for x and get an output. The range, which is about your y values, the range is not all real numbers, because you'll notice here that we don't have any negative y values. We only have from 0 and positive numbers. So 0 all the way up. This function never stops increasing. So this would go all the way up to infinity, from 0 to infinity. No negative numbers. That would be the range for your parent function of a quadratic. I hope this has given you some insight into what a quadratic function is, what the graph looks like, what type of equation gives you a quadratic function. I hope to end this video by showing you a few real-world examples of quadratic functions so that you can see that these are not just fancy graphs that we work with in math class, but that they have a lot of real applications. And if you start to look for these in the real world, I think you'll see them all over the place. I hope you've enjoyed this video. I've enjoyed making it. I'll see you guys in class on Monday. Have a great weekend.